Now it's time to do some exercises. First one, let omega equals the open ball center origin radius 1 contained in R2. Define u of x equals 1 plus mod log mod x power k, where 0 less than k less than half. Show that u belongs to H1 of omega. So we have to show that u is in L2 and its first distribution derivatives u du by dx1, du by dx2 are also in L2. So that's all that we have to do. So let us take integral over omega mod u square. So I will convert this into polar coordinates. Now it's a radial function, therefore there is no theta component. So when I integrate on theta 0 to 2 pi, I will pick up a 2 pi, and then I am integrating with respect to r. So 0 to 1, 1 plus mod log r power 2k, and then dx you will pick up r dr from the polar coordinate formula. Now repeated use of L'Hopital's rule so I will leave that checking for you, tells you that limit r tending to 0 mod log r power m into r equal to 0. Okay. So this means that if you expand this by binomial theorem, you get various powers of log r into r, all of them go to 0. So the function goes to 0 as r goes to 0. It's a nice smooth function otherwise, and therefore this implies that integral on omega mod u square dx is finite. Okay. So now we have to check what about the distribution derivatives. So here is like in the case of finding the fundamental solution of the Laplacian, we have to check if the distribution derivative is really got by the ordinary differentiation rules. So let phi belong to d omega. So we are looking at integral u d phi by dx1, let's say dx. And now, so you have omega is the unit ball, and the only singularity of the function is at the origin. So I remove a ball of radius epsilon, and therefore I have a remaining place omega epsilon. Now u is a L2 function on a set of finite measure. It's integrable. D phi by dx is a C infinity function with compact support. It is bounded, whatever you want, and therefore by the dominated convergence theorem you will have that this is nothing but limit epsilon tending to 0 integral on omega epsilon of u d phi by dx1. So let us look at integral on omega epsilon u d phi by dx1. Now we are all in smooth function case, and therefore we can do all calculus formulae can be used. So we use integration by parts. This is minus integral on omega epsilon du by dx1 of into phi dx plus integral on the boundary of omega. Now on the boundary of the omega you have, so you will get u phi into, because you are taking d by dx1, it will be nu 1, the unit outer normal. Now if you look at the outer boundary, phi is 0 because phi is a d omega function, and therefore that won't come in. So we only have to integrate on mod x equal to epsilon of u phi into nu 1. Now nu 1 is the nu is the unit normal, nu 1 is the first component because you are dealing with d by dx1, and that is nothing but x1 by r, x1 by epsilon. Okay, so now you have therefore integral on mod x equal to epsilon of u phi nu 1, okay, that is equal to, because the unit normal is minus x1 by epsilon, that will be minus integral x1 by epsilon for nu 1, and then but what is x1? x1 is nothing but epsilon cos theta, okay, by epsilon. So the whole thing will just give you cos theta, and then into phi into 1 plus mod log epsilon power k, and then you have to integrate from 0 to 2 pi, and you have epsilon d theta is the unit element of integration, because of the it is on a sphere circle of radius epsilon. So once again, cos theta, phi are all nice bounded functions, and epsilon log 1 plus epsilon power k will go to 0, and therefore this goes to 0 as epsilon goes to 0. And consequently, if you pass to the limit as epsilon goes to 0, you get integral on omega u d phi by dx1 dx is equal to minus integral on omega du by dx1 phi dx. So we have checked that the distribution derivative is the same as the classical derivative. So now, so r is less than 1 because mod x is less than 1. So u can be is nothing but 1 plus log 1 by r power k. So du by dx1 equals du by dr into dr by dx1, and that is equal to again du by dr into cos theta. Okay, so if you, so that is equal to k times 1 plus log 1 by r to the k minus 1 into r into minus 1 by r square. Log, when you differentiate, is 1 by 1 by r, that's why you get an r, and then you have to differentiate 1 by r, and that is give you minus 1 by r square and into cos theta. Okay, so integral of omega mod du by dx1 square dx is less than or equal to c times integral 0 to 1 of 1 plus log 1 by r power 2k minus 2 into 1 by r into 1 by r square into r dr, and the d theta I have squared it out. So this 1 by r here. Now if I put log 1 by r equal to s, so if you make this, so this will be equal to c times integral 0 to infinity of 1 plus s to the 2k minus 2 ds. Now you have k is less than half, so 2k minus 2 is strictly less than 1, and therefore this is a finite integral because the power exponent is strictly less than 1. It is integrable on the entire half of the real line. Okay, so this implies, so du by dx1 is belongs to L2 of omega. So similarly, du by dx2 is also in L2 of omega, and therefore you have that u is in H1 of omega. So this is just a straightforward exercise where we have to compute the distribution derivative and see that it is integral. Let omega equal to the open interval AB, and let A equals x naught less than x1 less than etc less than xn equal to b, and you set ij to be the interval xj minus 1 xj 1 less than equal to j less than equal to n. Okay, Let uk belong to H1 of ik for all k 1 less than equal to k less than equal to n. Define u from AB to R, u restricted to ik equals uk. Then show that u belongs to H1 of omega if and only if u belongs to C of omega bar. So, solution: if u is in H1 of omega, this implies that u is in C of omega bar. We have already proved. Okay. So, now conversely, let u defined as above belong to C of omega bar. Okay. And you take phi, let phi belong to d omega. Okay. Then integral a to b u phi dash dx is equal to sigma k equals 1 to n of integral on ik u phi dash dx, and now you do integration by parts. So, that will be minus integral minus sigma k equals 1 to n integral over ik of u dash phi dx plus sigma k equals 1 to n of u x k phi x k minus u x k minus 1 phi x k minus 1. Now, this term, the second term, vanishes, because if you write down fully, the terms will telescope. So, in fact, the second term equal to, just you will get u0 u of a phi of a u of b phi of b minus u of a phi of a, this whole thing, because all other terms, because since u is continuous. Okay, so u of xk is well defined. From whichever interval you come, you have this. Okay, and therefore, and this is equal to 0 because phi a phi b are both 0. Phi is C infinity with compact support, and therefore you have that u dash restricted to ik is equal to uk dash, and then, so since this implies that u dash is in L2 of AB, and that implies that u is in H1 of AB. U is anyway C of omega bar, so it is in L2, no problem. So, u is in H1 of AB. Okay. 3. Let omega contained in Rn bounded open set u in H1 0 of omega. Show that mod u of 1 omega is the same as mod u 1 omega. That is, the first derivatives of mod u, their L2 norm is the same as the first derivatives of u. Okay. So, solution, this is very easy. So, we know that mod u belongs to H1 0 of omega, we have seen this already, and d mod u by dx is nothing but sin u dxi is sin u du by dxi. Therefore, if you take integral on omega, this is mod d mod u by dxi square, this is dx, is the same as integral over u not equal to 0, sin u will be plus 1 or minus 1. So you will just get du by dxi square dx plus integral u equal to 0 d, that is it, because there sin u is 0. So this, but this is same as integral on omega mod du by dxi square, since on u equal to 0 du by dxi equal to 0 almost everywhere. This also we have shown, and therefore there is no new contribution from that side, because this function is integrand is 0 almost everywhere. So you can just add that, and so you will get this, and that completes the proof of this. 4. Let omega be contained in Rn, bounded open set. Let rho belong to C1 of omega bar. Show that u maps to rho times u defines a bounded linear operator of H1 of omega into itself. If rho is strictly positive on omega bar, show that this is an isomorphism of H1 of omega onto itself. So solution. So rho is in C1 of omega bar, implies bounded, implies rho u is also in L2 of omega. Now you let phi belong to d of omega. We have to check for the derivatives. Okay. Now omega, let support of phi be contained in omega dash, which is relatively compact in omega. You can always find this. So let un converge to u, un in d of Rn as in Friedrich's theorem. So integral on omega rho um d phi by dxi, we have to compute the derivative of rho u. Okay. So that is dx is equal to, because the support is in omega prime, I can write this as integral on omega prime rho d phi by dx. I am going to write a d by dxi of phi dx minus integral on omega prime rho of dum by dx I phi dx. Now the first term, this is equal to, I am going to use rho is C1 function, this is a smooth function, is in d of Rn, phi is in d of omega. So I can write this by integration by parts, minus omega dash d rho by dxi phi dx. There is no boundary term because support of phi is inside omega prime. So on the boundary of omega prime it will vanish, and therefore there will be no boundary term. Okay. Minus integral omega prime rho dum by dxi phi. So this implies that d by dxi of rho sorry, I'm going too fast. Okay, so then you pass to the limit, everything is fine, so you can use whatever result you want. So you get rho u d phi by dxi dx equals minus integral on omega prime. because I have the convergence of du by dxi in LP of omega prime, that will give you d rho by dxi u phi dx minus integral omega prime rho du by dxi phi dx, and now I will now go back to, that's equal to minus integral omega d rho by dxi u plus du by plus rho du by dxi phi dx, because again support of phi is contained in omega prime, outside there is nothing to 0, and this improves the d by dxi of rho u is nothing but d rho by dxi, the usual product rule, plus rho du by dxi. And since rho is in C1 of omega bar and its first derivative is also continuous on omega bar, so everything is bounded, so this belongs to L2 of omega. And then you have integral rho square u square is less or equal to C times integral mod u square, okay, dx on omega, and mod d rho by dxi again in L2 norm, this is less or equal to C times, which is about the bounds of d rho and dxi and rho, etc. And then you have L2 norm of u and L2 norm of du by dxi in by the triangle inequality, and that gives you less than norm u 1 omega. Okay, so this implies that norm rho u 1 omega is less than C times norm u 1 omega, and therefore it defines a continuous linear operator of H1 omega into itself. Now if rho is strictly positive on omega bar, this implies that 1 by rho belongs to C1 of omega bar, and therefore again that defines a continuous linear operator, multiplication by 1 by rho, and if V belongs to H1 of omega, V is equal to rho of 1 by rho V, which is also H1 of omega. So the mapping is onto, it is 1 1 onto continuous, and being in Banach spaces, open mapping theorem says, or anyway even otherwise, you know, with 1 by rho the inverse map is continuous, and therefore you have that it is an isomorphism.